Hi everyone. I wanted to come and share some techniques for working with chemicals in Python, using a combination of Google Colab pages and techniques that I've picked up over the last little while. Now I've made a GitHub Pages link up there. That's if you all just type in https://slatum, you probably leave the first bit out actually and just type slatum-talks.github.io/Resbaz, and I've made that so that it's easy for you to click the link to today's demonstration. So if you type this in, slatum-talks.github.io/Resbaz, then you'll get this page. Then if everyone just clicks here, we'll open up the actual Google Colab page. Now, before starting, we need to make a copy of this page in our own Google Drive account. So you can go to File and then choose Save a Copy in Drive, and it'll say creating a copy. And okay, here is the copy. And you see, for me, it says copy of participant cheminf QSAR demo. So once you've made that copy in your drive, some of you might need to log into Google first in your computer. Then you're ready to follow on with me as we go through the demonstration. So I've arranged this into chapters. Chapter 0, which is very Pythonic, to start with the 0th item. Chapter 1, getting the data. Chapter 2, a demonstration of fingerprints and what they are. Chapter 3, making a model, splitting into training and test sets so that we can make a model. And then chapter 4, what if I want to use the model again? So how to save the model and load it to test some new compound. And then chapter 5 is just a little afterthought. If we have time, I've got a bonus activity. So to start off with chapter 0, I reckon that computational methods in pharmacology and toxicology have matured. So it's not just some fun hobby in which I indulge, but in fact, lots of people are doing it, and there's been lots of successful models that are built. And that's evidenced by this latest version of ChemRes-Tox, which was a special artificial intelligence meets toxicology version. And my lab, we published a couple of papers in this edition, because as you can see, it's all about representing molecules in a computer, building some kind of computational model, and getting outputs to do things like adverse drug reaction prediction, including DILI, drug-induced liver injury. Fantastic. So I think it's really good fun. What are we going to do today? Today we'll perform the following steps. We'll get the chemical data from GitHub, calculate chemical fingerprints for those data, for the chemicals that are represented as SMILES structures, and generate a model to predict psychedelic activity. So I've based today's activity on this paper by Keshavarz, which looks at a method for assessing the psychotomimetic activity of substituted phenethylamines. And if anyone's watched Breaking Bad, you'd be pretty familiar with the term phenethylamines, or so they're phenyl structures with an ethylamine hanging off the end. And this paper, they looked at a whole bunch of phenethylamines and looked at how psychedelic they are by testing them in people, and well, the data that they used was from people, and they expressed the activity of each molecule as the log A, sometimes called the log MU, for mescaline units. That's the log of the activity in mescaline units, where the mescaline unit is defined as the ratio of the effective dose of mescaline to the effective dose of the tested compound. That means that a large value indicates more potency because the effective mescaline dose is divided by a smaller value, and so you get a bigger number. So if you need less of the test compound to get high compared with how much mescaline you need, then it's quite strong and you'd get a big log A value. Some studies look at other markers like 5-HT2A receptor binding, but I think this sounds like a lot more fun. So to start with, let's get the data and get started. So firstly, we download the data, and all you have to do here is run this cell in the Google Colab page. And so as long as you've got this copy of the ChemInfQSAR demo file in your Google Drive, the little drive there, then this should just run. And then the next cell, I've got a space indicated by these hashes. And so this is where you guys get to do some coding along with me. So we just type print df.info there, and we want to put df.info with open and closed parentheses or round brackets after it. And then the next line, we want to say df.head, and we'll just get the first two lines. So basically, let's find out about the data frame we've just created. It's df for data frame equals pd.read, that's pandas, read CSV, and we downloaded it. Now we want to have a look at it. And there's the df.info. It says we've got 114 molecules. We've got a column called number, name, smiles, and log A for the activity value. And there's the first couple. The next line says pip install RDKit. So unfortunately, we have to install RDKit every time we run this. And that's probably the only drawback to running stuff in the cloud. As you can see, it installs very quickly, so that's not really a big problem. Now, the next line has a couple of things for you to fill in. So I've got pandas dot tools. I wonder if I should have a capital P there. Pandas tools dot add molecule column to frame round bracket df comma smiles comma tick, and then molecule like that. And then the next line will be df square bracket, and then quotes smiles there, and then after that one we'll put in another one here, which is molecule, and then leave those two square brackets and dot head 1, and we'll run that. And is not defined. Okay. Now I have imported pandas. Maybe it just doesn't like the capital there. Oh yeah, that should be. It's funny that that even works, isn't it? Really? Pandas tools. Oh, it's not dot tools. So, okay, that's something that can happen. We don't read it properly, and it's pandas tools. Tools, what have I done wrong there? Pandas tools dot add molecule, ADD molecule column to frame df smiles molecule. Loves it. One thing about Python is you can't go around making any mistakes or everything breaks. So pandas tools, which we import there, you have to copy that exactly. And then, of course, the smiles, I had the column name down incorrectly. Okay, so the next line, so we've got our new molecule column is what we've done there. We're having a look at the new molecule column. We've said add molecule column to frame. Here's the smiles. Here's what to name the new column, and boom, there's our molecule column. And so now we want to check that RDKit can convert every molecule. So we just do a quick check here. It's always good to have some checks. So there's df.molecule dot isna open close round bracket, and then sum open and close. Oh man, sum open and close bracket, run, and it says 0. So it's happy that we're under control. Now what we're going to do is we're going to import NumPy to do some NumPy operations, and then we're going to define a function, and this is mol2fp. So that's a function that will convert a molecule object from RDKit into a fingerprint, and we're saying that fp equals get hashed Morgan fingerprint mol to number of bits 1024, so 1024 bits, and the 2 is for a radius 2 because the Morgan fingerprint is a radial fingerprint and requires us to say how far out from the atoms to look to describe the space of the sort of chemical space of the molecule as it looks around. So it's an ECFP, an extended chemical fingerprint, because it looks in a radius around. Okay, so we've got to have a look now, and so we'll check that the function that we've just created is working, and so we'll check that with the line here, fp equals mol to fp that we've just generated, open round bracket, chem dot mol from chem dot mol from smiles, and then open round bracket, df dot lock for location, square bracket 1 comma, and then in quotes smiles for the smiles column, and then we're going to say, okay, let's have a look at it. So again, as usual, I haven't typed it correctly. So mol to fp chem dot mol from smiles. What's that capital M doing there? Smiles. Let's see if that fixed it. Sure enough. So any tiny thing wrong with it and it won't work, of course. But if we said that fp equals run this function on the first molecule in the smiles column, then this is what we'd get. We'd get an array of ones and zeros, and that's what a fingerprint is. So the fingerprint is an array of ones and zeros that describes the characteristics of the molecules. Okay, so the next thing is we want to use the mol2fp function to generate fingerprints for all of the molecules in our data frame, now that we know it works. So we would say df square bracket fps for fingerprints, space equals df dot molecule dot apply bracket mol to fp, and then the next line would be df dot head to have a look at it. Let's see if it worked. And again, I've made an error. Oh gosh, I haven't put that in quotes, have I? So I need to obviously put the column name in quotes, and there's the new column name there, FPS, with each fingerprint as a whole lot of ones and zeros for the corresponding molecule. So now you're probably thinking, well, what are these fingerprints that we've just made? And so we go on to chapter 2 about fingerprints. So a fingerprint is a way of identifying all the characteristics of a model, beg your pardon, of a molecule. I'm used to saying model quite a lot, of a molecule. And there's an excellent description of them in this YouTube video from Greg Landrum, who invented RDKit. So I've got a couple of things to do here. Mol Listerhill's df molecule dot head 3 to list. That's just taking a few molecules from our data frame from the molecule column and adding it to a list called mol list. And now we can have a look at those in the next cell. So I've got all the imports there for our libraries that we need. And then finally, we just want to say, let's draw those 3 molecules that we've brought across. So head 3, just the 3 top rows. So we'd say img for image equals draw moles to grid image, moles to grid image, open round bracket, mol underscore list, the mol list we just made, comma, moles per row. Oh, it didn't like that, did it? Moles per row equals 3. And then the next line is simply img to say, okay, show me the image. Let's see if I've got that one right. And sure enough, there they are, lovely drawings of our phenethylamines, phenethylamine. There's the phenyl group, the ethyl group, and the amine group sticking on them. They are all different because we've got different halogens there on those 3. So the next thing is, let's take one of these molecules, take the second one, the 2,5-dimethoxy-4 chloroamphetamine, and we'll call that dimethoxy-4C for short. So under here we would say dimethoxy-4C, there it is there, dimethoxy-4C equals df for data frame, square bracket tick molecule, you have a look at the molecule column, and then square bracket 1. Run that, And that's generated a variable called dimethoxy4C, which takes the 1th molecule from the list. So that's the 0th one. That's the 1th molecule, and records that molecule as this variable. Now we will run the next bit, which is going to find which ones of the ones and zeros, which ones of the switches in the fingerprint are switched on. So if you run a Morgan fingerprint of this molecule and get a list of ones and zeros, which we see up here, where are we? Up here, this list of ones and zeros. What this code does is it says, well, which ones of those ones and zeros are switched on as ones, indicating that the bit is on and the feature exists. So this is how to understand what fingerprints are actually doing. This is the list of the ones. There aren't that many, and it just says which of that list of ones are switched on. And what we're going to do next is draw the part of dimethoxy4C that corresponds to the on bits. So the first line here, we're going to say prints equals square bracket, round bracket, dimethoxy4C, comma space x, comma space by 4x in FP dot get on bits. There it is there. Get on bits, open close parentheses. And then the next line is draw Morgan bits, draw Morgan bits, open round bracket, prints, comma, moles per row equals 4, moles per row equals 4, comma space, legends equals square bracket str for string of the x space 4x in FP dot get on bits. There it is there. Get on bits. And it's got an open and close parentheses as well. And let's see if we got that right. Gosh. So it doesn't like that. So we've got draw Morgan bits prints moles per row equals 4, comma space legends equals str x 4x in FP dot get on bits. I've accepted an automatic thing there, but it's get on bits, not get num on bits. So let's try that again. And there we are. Aren't they beautiful? So this output shows all of the bits that are being detected and are allocated this point in the fingerprint. So the 1007th point is indicated by the presence of this structure and so forth. So there's simply a carbon with 3 things bound to it on one hand, and then there's like much more complex structures, as you can see, that are being picked out by the fingerprint algorithm. So now we want to extract fingerprints into a separate column for modeling. Where are we? extract the fingerprint column for modeling. And so this is FP underscore DF equals DF square bracket FPS, oh gosh, square bracket, and in quotes FP and little s. There it is there. Dot apply round bracket PD dot series. And the next bit is FP underscore DF, dot head 2. Let's see if we got that one right. Oh, so all we're doing here is just applying the PD.series to the FPS column and extracting that out into an array of rows and columns. So that's pulled out the whole FPS fingerprints column and generated a new data frame called FPDF. So it's a fingerprint data frame with all the fingerprints in it. It's 1024, so from the 0th column up to the 1023th column, which is obviously the 124th column, counting from 0. And then we want to bring back the log A column, the outcome column. So we'll do that here. Boom, there's our log A column. We also want to bring back the name column so we can see who are these molecules. So we do that. There's name. And so now we've got the name and we've got the fingerprint and we've got the activity. So now we're ready to go ahead and make a model of this data so that hopefully we can predict activity of some new molecule that we've never seen before. So we'll open up chapter 3. And to start with, we'll load a data frame with all the fingerprint values for the X, for the descriptor values. So X will be all the fingerprint values, and Y, the thing we're predicting, will be all the log A values. So to start with, we'd say X equals FP underscore DF dot iloc square bracket, and then full colon, all the rows, and then comma, and then all the rows, and we want columns 1 to 1025. Okay, so that's 1 to 1025 because we put the name in there. So we're not starting from the 0th one. We don't want the name, and we're going up to 1025, which will take us up to the 1023 because the name and the 0 column. And then for the Y, so Y equals FP underscore DF square bracket, and then tick log A, which is the name of the output column, and dot values. We want the values. So let's run that and see if that's okay. And then we'll show the first 2 lines of X. So that's X dot head 2. We do that and we can see, sure enough, 0 to 1023. And then what about Y? Well, we can do Y dot shape and run that. And it says there's 114 items, which is what we would expect. So the next thing we will do is split the data into training and test data sets here. So that'll be X train, X test, Y train y test are the sets, and that'll be equals train underscore test underscore split to use the scikit-learn built-in train test split algorithm. And so we then feed that with the X and the Y, and we'll say test underscore size equals 0.15 for 15% test set. We run that, and so now that has made our training and test sets with sets of X's, the descriptors, and sets of Y's, the answers, with 15% of our original data set being put aside as the test set with those test X's and test Y's that we can test on. So now we're ready to make a model. And because this is a regression problem, we're going to use RFR, which is random forest regressor, equals random forest regressor. And then we'll say random underscore state equals 42. A lot of people use 42 for this from Hitchhiker's Guide to the Galaxy. And then RFR dot fit X train Y train and run that. See how that goes. Oh, I've done something. So I've got random forest regressor, and it didn't like random state. Random state. Yes, it's my dyslexia coming to the fore, but there we go. Random forest regressor, random state 42. You just give it a particular random state so that every time you run it, you get the same answers. So it's not starting from a different random seed each time. So now we're ready to have a look at the performance in training. And so in order to do that, we need to say that y pred, the predicted y values, equals RFR dot predict, there it is, RFR dot predict X wait on. Oh, what have I done there? Oh no, I must have that right. Dot predict X test, there it is. And we go. And so now we've got the performance. So we've got score equals RFR dot score X train Y train print R squared score, and then Y pred equals RFR dot predict X test, and so that gives us the test prediction values of how well is it going on the test set. And then finally, we'll now plot this and see what that performance, what that model performance looks like as a plot in Matplotlib. So to start with, we just say X equals Y test and Y equals Y pred. So Y test versus Y pred. That's what we're going to plot against each other. Then we'll draw a line of best fit with polyfit. So that's A, comma B equals NP. I'm recording.
Oh, sorry.
NP dot poly, go away. Poly fit.
Sorry.
X, Y, 1. And that just generates a line of best fit through the data, plotting our predicted versus our actual log A values. And there it is. There's our line of best fit. And as you can see, that does pretty well. So finally, just to print the test set R square value, the test set R square value, which is the square of the correlation value, using the NP dot correlation coefficient for X and Y, and we get the test set R square value of 0.78. So there's a strong correlation there. So it does a very good job of predicting. The training value, of course, was 0.94 R squared. And of course, you'd expect the test value to be a bit less good. And that's what you see, 0.78. Now, finally, what if we want to use this model again? Well, it's quite simple. We just use a library called joblib, or job library, joblib. We'll put job lib there, dot, bloody hell, I'm all flustered, dump RFR, and then we'll give it a name. So P S Y key delix dot PKL for pickle. So we used joblib to dump the model as a pickled model for later use. Then if we want to load it again, we use joblib.load. And then if we want to test it again, we use m equals mol to FP of m dot mol from smiles. So chem.mol from smiles, and then test underscore SMI, as we're going to declare up there. That's what we're going to be testing on, test SMI for test smiles, and then just M here, so we can have a look at it. And so there is the array. So I've said M, give us a look at the array, and that looks like that. That's its fingerprint of this simple molecule here. And then we just say model dot predict round bracket, square bracket, M, and we get the value 0.4. So that's our predicted log A value for how potent this would be using this model. And of course, the model is not perfect. There's loads of things that you could do to improve, and I've written words to that effect here. Of course, the code above is only a demonstration. There's a million different ways that you could improve this, putting in more data, representing the molecules with different fingerprints, chemical descriptors, density functional theory, so quantum molecular characteristics could be used to get a better idea of the behavior of our model. And then there's all the different ways that the model can be tested for being sure that it is able to perform in the future. The best possible way would be to collect new data and run the model testing that. Now, if we've got time, we'll go into this bonus material. So if we've got time, go into this bonus material using a thing called PubChemPy. So we can just play with PubChemPy for a moment. First, we install it. And then I've given you a molecule. Here's a molecule to play with. So we create a variable called smiles, and that's with our new molecule. And now we want to see, okay, what is this molecule that you've given us? So we would say here, mol equals chem dot mol from smiles, and then open bracket, tick, and I'm just going to copy this smiles from up here and put it in there, and then here we'll just say mol so we can have a look at it. So there's our molecule that I've given you. You don't know what I've given you yet, but now you know what it looks like. So now we can import PubChemPy as PCP and get the compound information from the smiles. So the only bit I've left out here is the bit where you say, okay, what's the drug we're looking at? So drug equals PCP, which we've just declared, import PubChemPy as PCP. So drug equals PCP dot get underscore compounds smiles, which is what we're you have to say what is it that you're giving me. So we say we'll give you a smiles. So the first one's the capital smiles. That's because we've generated a thing called smiles up here. And then the second one, so this is what we're passing to it. And the second one is where we say, this is the format that we're giving you. So once we've declared that, we run it. Oh, okay, I've given you cocaine. Well, I suppose you probably needed something to perk you up after taking all those phenethylamines. Okay, that concludes this demonstration. So I'll just stop now.